going to be talking about how to balance reactions. But before we do that, there are some symbols noted in the reactions themselves that you may not know what they mean. So we're going to go over and outline them, okay? Looking here, as you can see on number 1 here, there is a little S symbol right here next to this compound, like so. Okay? Does anybody have any idea what that might represent? What is it telling us about the KClO3, the potassium chlorate there? Anyone? No, it's not synthesis. It's actually telling us something particularly about this one compound. That it's a solid. Very good. That's exactly right. So its physical state would be in that little parenthesis there next to it, telling us what type of physical state we've got. So if you see an S right next to it, you would note that this is going to be a solid. So I'm sure you can now figure out what the L might mean. Liquid. Very good. Exactly right. Okay. And G, yes, is going to be the gas. Very good. Now, how about what does AQ mean? Or what do you think of when you see AQ? I think of water. Good, because that's what you should think of. It means aqueous. So, something to do with water. What could it be? We have, it says AQ next to it. We know that compound is what?
Water.
It's a compound with this next to it. So it doesn't say H2O. That particular compound is what in water? Dissolved in water. Okay, it's in solution. AQ means it's been dissolved in water and it's in solution. And yes, acids would be represented with AQs next to them because that means that hydrogen ions are floating around in the water. Okay? So aqueous means that it's been dissolved in water. Okay? Now I know that mine's missing it up top there, but here we'll just put it right here. What do you think a plus sign means? Well, yes, it could mean positive, but in a reaction there where we have a left side and a right side and an arrow, what do you think the pluses mean? Adding together on the reactant side. On the product side, it's just showing you that you get two products if you have a plus sign between them. So you get something and something, okay? So that means that they are added, or it's going to separate your products. Okay, it means that they're going to be reacting with each other, or it's separating the products, okay? Now, does anybody know the technical term for the arrow? What does that mean? Besides producing products, it actually has a term that we use to call the arrow. It means yields, okay? So the reactions are going to yield the products, okay, which also we would say means produces. My user is not coming out right. Okay, so yields or produces, the arrow's technical term is yields. Now, an up arrow like that next to a compound. On the right-hand side of a compound, you might see a little up arrow. What might that signify? Something floating up in the air? And what could be floating up in the air? What kind of substance will go floating up in the air? Ah, gas. So it means the gas is like bubbling off. Okay, so you're getting a gas there. It's bubbling off. Oh, I forgot to address our delta or heat. Now, if you have an arrow here, you could have a delta sign above the arrow, or you could have the word actually heat written above the arrow, or you could have heat, plus a reactant going to a product or something like that. So you can see heat pretty much anywhere in the equation. And remember, as we discussed before, if you add heat in, it's going to be endothermic. And if you have heat as a product, where it's releasing energy, something like this, okay, then it would be exothermic. And we're going to go into endo and exo again later in this unit. But heat could be somewhere in there, because a lot of times to get reactions going and started, you either need to add heat in because it requires it to get it moving, or sometimes it's going to produce heat. And we know which ones produce a lot of heat. What type of reactions produce a lot of heat?
Exothermic reactions.
Yes, but out of the types that we discussed last class.
Fire.
Well, what kinds produce fire?
Combustion.
Combustion. Very good. Combustion reactions produce lots of heat, so they're always going to be exothermic. Okay? So if you see those, that's what they mean in the reactions. All right, now, another thing over here, what a catalyst will look like. You might see an arrow like this, and it might have a compound above it, like so. That compound is a catalyst. It's not actually part of the reaction. It is helping to speed up the reaction. Okay? So you can have catalysts in there, but they don't actually change with the products or the reactants. They stay the same throughout. Yes? Well, no, technically in the ice pack, they keep the chemicals separated, and then when you break them, they come together, mix, and then you get the cold. So, and same thing with those glow sticks. Till you break them, then the chemical reaction doesn't start. But there isn't really, I think, a catalyst in there because those reactions just happen on their own. Well, you don't want to get the chemicals on you, no. Yeah, really. Last but not least over here, if the up arrow signifies a gas bubbling out, what might a down arrow mean? Forming a solid, and particularly we call this kind of a solid a special name. Remember at the beginning of the year when we had the two test tubes that were clear liquids and put them together and it came out to be like this purple stuff falling to the bottom? What did we call those? Stuff that would fall to the bottom as crystals? A precipitate, thank you. So yes, we would have a precipitate. And precipitates are solids, yes. Okay, so if you see these symbols now, you know what they mean when you look at a chemical reaction. And now for balancing. Let's talk some balancing. Why must we balance a chemical reaction to begin with? Anyone know? It is a law out there. Law of conservation of mass or matter. Good. Energy is another one. It doesn't pertain here, but both state basically that it can never be what? Never be created or destroyed. It just can be altered. You have a certain amount to begin with, you're going to have a certain amount to end with. And it can change and form new bonds and be new compounds, but it doesn't disappear, nor does it get created. Okay? So, law of conservation of matter or mass. So, that means if I start out with 3 hydrogens, on the other side I need to have 3 hydrogens, right? They need to balance. But also the masses must be the same too. So keep that in mind. If I were to have, say, 25 grams in my reactants, guess what? Over here in my products, how many grams should I have? 25 grams as well. Okay? So the masses should be conserved regardless. So you might have one reactant that's 8 grams and the other reactant might be 17 grams. And on the product, you might have two products and one's 10 and one's 15. But they should both add up to 25 when you do the final tally. Okay? So masses should be conserved and atoms amounts should be conserved. All right? So, and some of these are trial and error. I'm going to show you my way of how to do balancing. And on this particular packet, I expect you to show the work and do all that. On the next couple of practices that you get, though, if you can eyeball it and do it in your head, you don't have to show me all the work. I just want it for this particular one because I give you some strategies here that make it easier to balance some of the more difficult ones. Okay? So we're going to work through a couple here on the front. Then I'm going to work through a couple other types. And we're going to save organic combustion for last because that's the hardest. Okay? So let's look at this first one. First of all, what type is number 1? What type of reaction? It is a decomp. Good. Decomposition. Good. Now, what I do here, right around where the arrow is I make a nice little tic-tac-toe board. And you make it for how many elements that you have in your reaction. So I have K, I have Cl, and I have O. Now this side, I'm going to tally up my amounts of reactants. Over here on the right, I'm going to tally up my numbers in my products. Okay? So I do my tallies first so I can figure out who's not in balance, who's out of balance, who doesn't have the same amount. Okay? So on this side, how many Ks do I have on the reactants? 1. How many chlorines? 1. And then how many oxygens? 3. That's correct. Over here on the product side, let's do our tallies. How many potassiums? 1. How many chlorines? 1. And how many O's? 2. Good. Now that we have that set up, we can figure out who's out of balance. And which element is not balanced? Oxygen. So we need to fix our oxygens here. In this particular case, we kind of have a weird arrangement. We've got a 3 and a 2. We have an odd number for one side. Now, is an even number ever going to balance out with an odd number? No. So we have to go kind of for this idea of the least common multiple. So a 3 and a 2, what is the least common multiple between them? 6. So I'm going to try with the 6 and see if that works. Sometimes you have to erase and start over, too. So don't get frustrated. It may take a couple times. So if I'm going to use the 3 and the 2, if I put what number in front of the O2 there, can I make it have 6? If I put a 3 here, this means it's going to have 6. Good. Right? And I just cross off the other one and I do my new tally next to it to keep track of my numbers. So it's easier for me to visually see my numbers. So over here, what do I do on the reactant side now to fix the O to make it a 6? I put a 2 in. Remember, we're inserting these things called coefficients. The coefficients are the only things you can do to change the balance reaction. You can put a coefficient in, but it has to be in front of the entire compound. Can't be in the middle of it. It has to be in front of the entire thing.
Now, K, C.
Correct. Well, our O's go up to 6, but you are correct. The K's and the CL's now have all changed. Because this was once a 1, now you have a 2 in front of it, it becomes a 2. This one was, the CL was once a 1, and now you put a 2 in front of it, it now is a 2. Correct. We do need to fix the other side. So you might have to go back and forth from side to fix them. So it is an easy fix though, because what can I put here to make this one have 2 CLs and 2 Ks? If I just put a 2 here, that will go to a 2, and that will go to a 2, and guess what? I'm done. So really what your final answer is this top part with the coefficients. That's your final answer. Okay, that's what you're trying to do, is insert the coefficients correctly where they're supposed to go. This is just the extra little tidbit of work to be able to keep track of your numbers, because it is hard sometimes when you're not keeping track. Let's look at number 2. What kind of reaction is number 2? It's a decomp as well. Good. So this one only has 2 elements in it, so that's nice. That's easier, right? So I have my Pb and I have my O, my lead and my oxygen. So I do my tallies, my reactant tally and my product tally. Over here on the reactants, over here on the products. How many leads on my reactant side? 1. How many oxygens? 2. Now be careful over here on the product side. How many leads?
1.
How many oxygens? Good. There's a 1 here and a 2 here, so that adds up to 3. Well, would we do the same thing as before? They're in separate compounds now. We have the O's in separate compounds. Is there another way we can balance it out by putting something in front of our lead 2 oxide here in order to make that one an even number to work with? Yeah, if I multiply this by a 2, that now makes this side a 2. So 2 times 2 plus 2 gives me 4 oxygens, right? But it also altered my leads, because lead now is a 2, because 2 times the 1 here makes it have a 2. But yeah, now it conveniently makes it set up for the other side to work out. Do you see that? Because now on the other side, all we have to do is put what here to make it work out? A 2. If we put a 2 here, 2 times our understood 1 gives us a 2 here. 2 times the 2 from the oxygen gives us a 4 here. Is everybody equal now? Yes, so now we would be balanced. Now, one other thing to point out about the SOL. Here, we don't put anything in there when it's just a 1. It's an understood 1. However, on the SOL, they usually give you these little like keyboard thing of numbers, and they want you, it's one of the TEI questions where they want you to click and point them over. Okay, so you would insert your coefficients into the right slot. You wouldn't leave one blank, so you would want to put a 1 there. So on the SOL, if you are balancing it over, you do need to insert the 1 there. On ours, we just leave them blank because we know it's an understood 1. Okay? We'll go over those TEI questions closer we get to the SOL, but do understand that that means an understood 1 there. Okay? So now I'm going to progress on to the next page where we have different situations that we can apply here. So that's 2 possible scenarios you might see. So let's look at one where we have polyatomics involved. Let's scroll down here. Like, say, 8. Let's do number 8. What type of reaction is number 8? What type of reaction is number 8? It is a single replacement. Good. SR, single replacement. We have an element plus a compound, giving us a compound plus an element. The copper and the silver are switching places. Good. So that's a cation switch for a single replacement. Now, when I'm balancing these guys, if I have a polyatomic on both sides, like so, I can keep them together as a group. I don't have to separate them. It makes it a whole lot easier. So when I do my chart, Cu, Ag, and NO3. I keep the NO3 together because it's on both sides. I'm allowed to do that. Okay? If it's not on both sides, you have to separate it into its elements, though. Okay? So let's do our tallies. How many coppers on the reactants over here? 1. How many silvers? And how many nitrates?
4.
No parentheses means there's just 1. Yes. Over here on the product side, we have copper, 1. How about the nitrates now? That's 2 groups, because the 2 outside the parentheses means 2 groups of nitrate. And we have 1 silver, right? So who's out of balance? The nitrates. So let's fix those. What can I put here to fix my nitrates? I put a 2 here. That makes my silver go to 2 though, and my nitrates go to 2. So I fixed the nitrates, but then I kind of messed up the silver, so let's fix the silvers now. What do I put over here to fix the silvers? 2. And now, is everybody in balance? Yes, so when you have polyatomics on both sides, you can treat them as groups. Okay? Now for the most confusing of all, well, besides combustion, because combustion is kind of hard. But the other confusing one is neutralization. So let's look at the one at the top, which is neutralization. How do I know number 4 is a neutralization? I have a base. Yes, KOH is a base. H3PO4, what kind of acid is that? What's its name? Well, that's potassium hydroxide is the base. What's the H3PO4 though? What kind of acid? What's the name for that? Phosphoric acid, because remember it comes from phosphate and H changes to ic here. So phosphoric acid. We get our potassium phosphate, which happens to be our salt. And we get water, always as a product here. So this must be neutralization. So some of you labeled this as double replacement, but you would need to label it as neutralization as the specialized type of double replacement there. The salts will be different occasion, you know. No, for balancing, yes, we do something different here. To make it easier on ourselves, we have an OH group over here, and we have an H group here, right? So what can I do to my water to make that work? I can change my water to an HOH, right? 2 H's, 1 O, still the same thing, but now I've just put it into 2 separate groupings. I make it an H group and I make it an OH group. Now I can compare to the other side. Does everybody see that? HOH. Okay? So now when I set up my chart to do my tallies, I can keep it in order because they get really confusing trying to do the H's and OH's in this unless you separate them into their groups. Yeah, you're separating it into a hydrogen group and a hydroxide group. Exactly. So here, let me do my little chart. So I get K, I get OH, I get H, and I get my PO4. That still didn't come out as well as I'd like it to. Let's fix that. There we go. Better. All right. Now let's start doing our tallies. On the reactant side, what do we have? 1K, 1 OH. How many H's though? 3, and how many PO4s? 1, because there's no parentheses. I know it's a 1. Over here, how many Ks? 3 Ks, 1 phosphate, 1 H, because we're treating this as a group, and 1 OH, because we're treating that as a group. Right? 2 separate groups. Now, let's fix. What do we want to fix first, the Ks or the H's? We can fix both, but which one do you want to start with? Let's fix the Ks first, sure. So what do I put over here to make my reactants have 3? Put a 3 up here, good. So that changes the Ks to a 3. But what does that do to my OHs? It does make it have 3. So over here, now we need to fix our OHs and our H's. So if we put a 3 here, guess what? Everything works out nicely. Now you tell me, would you have been able to visually see that if it was written as H2O to make those two coincide together? That's why we change only in neutralization to this only applies to neutralization. You change it to HOH when you have a H group, hydrogen group, and a hydroxide group to compare to. Okay? So keep that in mind. So what I would like you to do right now is balance a few, but skip all the organic combustions. Like 6 is an organic combustion, so skip that one. Don't do organic combustion yet. Do some practice, and we're going to come back in a minute and talk about organic combustion. You to go to the back page where you have the little bit of space kind of near your snail from today, your snail stamp. Okay? So, I'm going to give you a set of rules to follow for combustion to make it easier, but you have to follow them. Okay? So, I'm going to give you an example here for combustion. We're going to do C5H10 plus O2, not water, O2. Water is one of the products. Let's go here. All right, CO2 plus H2O. So we know this is combustion because we have a carbon compound. We know we have oxygen as the reactant. Says you need oxygen in order to burn, and you produce carbon dioxide and water. So I am going to set up my little chart here. We call it the CHO, C-H-O. But step 1. Well, first let's put in our numbers. I forgot to do that. Let's do that. 5, 10, and 2. Over here we have 1, 2, and for our oxygens, don't forget you have some in your carbon dioxide. You do have an oxygen in your water, so that actually becomes a 3. So those are our numbers we have to begin with. Quite off, lots of them quite off. So the first step, balance carbon. Balance carbon. So that's what I'm going to do. I'm going to balance carbon. Look over here. We have 5 and we have 1. So what do I put there in order to make it have a 5? A 5. Very good. So now that becomes a 5. I'm not doing anything else yet. Second step. I'm going to balance my hydrogens. So, over here, I have 10 on my reactant side. I need to have 10 on my product side. What do I need to put there? 5 times 2 will give me 10. Good. So we're going to put a 5 here. And I'm going to make that a 10. Good. Now, this is where it gets a little different. Third step. Add up the oxygen atoms on the product side. So let's add them up. We have 5 times 2, that gives us 10, plus 5 times 1, that gives us 5, that's a total of 15. Correct. Everybody see that? So this turns into a 15. Now, we have O2 over here to work with. So this number needs to be doubled in order to get us the right answer. So the fourth step is actually taking our number here. Okay, fourth step. Divide the oxygen number by 2. Divide the oxygen number by 2. So if I divide this by 2, what do I get? 7.5. Okay? So 7.5 is not a whole number. And yes, that's a problem, but I'm going to stick it over here just for now. Kind of small. Just for fun. Let's stick it there. Does everybody see, though, over here, 7.5 times 2 would give me 15? Right? Does that make sense? Okay. Now, because we're not allowed to keep 0.5s in there, it's got to be a whole number. We are going to do kind of what we did in the empirical molecular formula cases where we got 0.5s. We will multiply until whole. So what can we multiply by 0.5 to make it a whole number? 2. But what we do to one of the substances, we've got to do it to all of the substances. So if I multiply this I'm going to multiply this by 2. So I'm going to multiply everybody by 2. So this guy now gets a 2. This one becomes a 15. This one becomes a 10. This one becomes a 10. Everybody gets multiplied by 2. Now, if you get an odd number, so that would be step 5. But you only have to do step 5 if you get an odd number. If you get an even number, you just stick it in front of the O2, and you're done. Okay? But if you get an odd number, basically a 0.5, when dividing here, then multiply everything by 2. You get that odd number, which ends up making us have a 0.5 there. Then we multiply everything by 2. So, in lieu of that, let's try 26 right now. Sorry, you probably still need to read that. So everybody try 26, because that is a combustion one. So do these steps right now that you just did.